Now, one question that you're probably asking yourself is, if we're trying to test a joint hypothesis, for instance, beta 1 is equal to beta 2 is equal to 0, why can't we just test the individual t-statistics on beta 1 and the individual t-statistic on beta 2, and if we reject the null for either of those cases, why can't we just reject the null that beta 1 is equal to beta 2 is equal to 0? Well, in order to illustrate this, let's consider an example. So let's suppose you're trying to estimate the relationship between y, x and z, and you want to test the null hypothesis that neither x or z have any impact on the dependent variable y. Now that's equivalent to saying that beta 1 is equal to beta 2 is equal to 0. So our null hypothesis here is that beta 1 is equal to beta 2 is equal to 0. Now we want to reject that null hypothesis if the null hypothesis is true 5% of the time. We want the significance level of our test to be 5%. So in other words, we want, if the null hypothesis were true, to only reject that null hypothesis 5% of the time. Now, one method that we've suggested is simply to calculate the individual t-statistics for beta 1 and for beta 2, and if either of these cases we get a t-statistic greater than 1.96 in magnitude, we reject the null hypothesis. So what do we know already? Well, we know that if the null hypothesis is true, so in other words, if beta 1 is equal to 0, the probability of getting a t-statistic greater than 1.96 in magnitude is equal to 0.05. Similarly, if beta 2 is equal to 0, the probability of getting a t-statistic greater in magnitude than 1.96 is also 0.05. So just to review t-statistics, remember, if the null hypothesis is true, the probability of you ending up in the rejection region is going to be equal to 0.05. So the probability of you getting a t-statistic greater than or equal to 1.96 is 0.05. 5% of the time you end up in that rejection region. But that's for an individual t-test. Here we're effectively carrying out two t-tests. So in this strategy that we suggest, we're going to construct a t-statistic for beta 1. We're also going to construct a t-statistic for beta 2. And suppose that our strategy is to reject our joint hypothesis, so in other words, beta 1 is equal to beta 2 is equal to 0, if we reject the null in either of these two cases. So in other words, if we're in this region, or if we're in this region, or in this region, or that region, if we're in any of those four rejection regions, we're going to reject our null hypothesis. So in other words, we're wanting to find the probability of the magnitude of our t-statistic on beta 1 being greater than or equal to 1.96, or the magnitude of our t-statistic on beta 2 being greater than or equal to 1.96. Now, we know that 5% of the time, if the null hypothesis is true, so in other words, if beta 1 is equal to 0, we'll get a t-statistic on beta 1 greater than or equal to 1.96. Similarly, 5% of the time, if beta 2 is equal to 0, we'll get a t-statistic with magnitude greater than 1.96. So if we wanted to find the probability of getting a t-statistic on either beta 1 or beta 2 being greater than or equal to 1.96, if both of them in reality are equal to 0, then we need to find the total shaded area. And the total shaded area is going to be equal to this probability that T1 is greater than or equal to 1.96 plus the probability that T2 is greater than or equal to 1.96. But we're counting the intersection twice. The intersection, which is the probability that both are greater than or equal to 1.96. We're counting that area twice. So if we wanted to find the probability of us rejecting the null hypothesis here when the null hypothesis is actually true, so in other words, when beta 1 is equal to beta 2 is equal to 0, it's going to be equal to this area plus this area, so the probability that the magnitude of T1 is greater than or equal to 1.96, plus the probability that the magnitude of T2 is greater than or equal to 1.96, minus the probability that both are greater than or equal to 1.96. So in other words, we need to add the red area plus the blue area and subtract the intersection. So let's make a very strong assumption. Let's assume that beta 1 hat and beta 2 hat are independent. Why are we doing this? Well, we're doing this because it makes the maths easier. So if we wanted to find the area of that intersection, if beta 1 hat and beta 2 hat are independent, it also will follow that the t-stats are also independent. So the probability that t1 is greater in magnitude than 1.96 and t2 is greater in magnitude than 1.96, we can just look at the product of the two probabilities. So 0.05 times 0.05, which is equal to 0.0025. Now, if we wanted to find the probability of us rejecting our joint null, if we were using this strategy, then we'd add up the two probabilities, 0.05 plus 0.05 minus the intersection, because remember we're counting that intersection twice, and that gives us 0.0975. So if we're simply looking at the individual t-statistics and comparing those individual t-statistics with 1.96, then we're rejecting the null hypothesis more than 5% of the time when the null hypothesis were true. So if the null hypothesis were true, remember, we're saying that beta 1 is equal to beta 2 is equal to 0. Yet if we simply look at the individual t-statistics and compare those individual t-statistics with 1.96, and if either of them are greater than 1.96, we reject our joint hypothesis. We're rejecting that joint hypothesis more than 5% of the time. We're not working at the 5% significance level. So there are a number of solutions. One solution might be to try and construct a different set of critical values. But in order to do that, we'd need to know precisely the joint distribution of beta 1 hat and beta 2 hat. And that's going to change depending on the relationship that you're estimating. So an easier solution might be to examine the R-squareds. But as we're going to see in the next session, whenever we add in additional explanatory variables, the R-squared is always going to increase. So we need to have a metric which will allow us to try and compare specifications where we look at whether or not including these additional variables genuinely improves the model. And the test that we end up developing, and we'll talk about this in session 10, is known as an F-test.